Hello friends, today we'll be doing a brief overview of the topology of the controller. From there we'll spend the rest of the series going over each individual block in more detail. We start with the three-phase inverter. This is the heart of the system. Its job is to convert the DC voltage from the battery pack to three-phase AC. We'll talk about exactly how it works in more detail, but generally what it does is it turns on and off an array of switches in a manner that replicates our desired AC signal. It's very similar to something like a digital amplifier, such as the Class D amplifier. There's a couple other components along our high power path that are worth noting as well. So there's a DC link capacitor, which acts as a mini power source closer to the inverter. All wires have some form of inductance. Inductance is basically the opposition to the change in current, similar to how resistance is the opposition to current. The further away from the battery pack the inverter is, the greater inductance we have between our power source and the inverter. This inductance prevents the inverter from receiving the current it needs, so we end up seeing ripples on the output. The capacitor acts as a low inductance path to the inverter. This is similar to bypass capacitors. In low voltage designs, the battery is usually quite near, so these capacitors don't need to supply a whole lot of current. With higher voltage or generally bigger battery packs, such as EVs, the capacitors end up being relatively large compared to the rest of the system. Additionally, in high voltage designs, we have to make sure that the capacitor discharges itself after it powers off. For low voltage designs, this isn't as big an issue, but with higher voltages, we of course want to make sure that there's no accidental injuries. One thing to note is that we can include additional filtering on the output in the form of LC filters, but these typically aren't found in battery-powered applications. They end up taking a lot of space and weight, and we don't really need the cleanest power for our motors, so they aren't really used, but they will be found in things such as solar inverters. So the next important piece is the microcontroller. This is the brain of the system. It's primarily responsible for generating the control signals we need to generate the state of this, or to change the state of the switches in the inverter. These signals are usually found in the form of pulse width modulation, or PWM. The simplest implementation is called open loop, where we just tell the inverter to generate a fixed frequency output. This usually isn't good enough. We want to be able to adjust exactly what we're feeding to the motor to control things such as speed. As we talked about before, in a synchronous motor, we'll also usually want to monitor the position of the motor. Note that many low-powered motor controllers use something called sensorless control, which skips over the position sensing. So the microcontroller, or MCU, is responsible for taking in data from these sensors and making the appropriate changes to the signals that we end up feeding to the inverter. Finally, the MCU is also responsible for communicating to external devices. In more complicated applications, this communication is usually CAN bus. It's a serial communication protocol that's similar to USB and can send a whole lot of data to other devices. In less complex applications, we usually just talk to the MCU using a PWM signal. And finally, we'll also have some sensors that we use for the sake of protection. For example, we can set a minimum input voltage threshold so we don't over-discharge our battery. We might also want some temperature sensors or something to make sure our power lines aren't getting too hot. And sometimes we'll need position sensors or current sensors in our control loop. The current sensors can also help make sure we're not drawing too much power from our battery. It's not illustrated here, but we can also monitor voltage on the DC side or current on the voltage on the AC side or current on the DC side. And the last piece is the gate driver. The gate driver is responsible for amplifying the microcontroller signal. In many cases, we need the control signals to feed the inverter to be relatively high voltage and current, usually around 10 to 20 volts, and in some cases upwards of multiple amps. So the gate driver is responsible for taking that signal from the MCU and outputting it at the voltage and the current that the inverter needs to function correctly. In high voltage applications, we might want other features such as isolation to protect the low side from the high side. So gate drivers will have some kind of built-in isolation barrier. This should make it impossible for high voltages to accidentally jump over to the low voltage side, at least assuming the rest of the PCB is designed to specification. We don't really need this isolation in low voltage designs. And that's about it for this video. The next few videos will be going more in detail about the three-phase inverter and exactly how we can control it to convert from DC to 3-phase AC. See y'all there.